So how many of you have heard of the ghost vulnerability? Quite a few. Okay, so that is something that we worked on pretty recently, and it's a pretty serious threat because it allows it makes all Linux machines vulnerable and can allow remote code execution or an attacker to basically take complete control of your system remotely if you use a certain set of functions. So anyway, this talk is not about the ghost vulnerability. I was just pitching that in to let some people wait for some people coming in. If you want to find more details about it, you can go to laws.college.com, or if you want to find about the exploit, then I guess the only way is to get me really drunk here tonight, and then maybe, yeah, you can get to that. So what does this talk about? So this talk is about anatomy of a POS malware. So a POS is basically a point of sale system. A typical POS looks like the one that you see in front of your screen right now. And the short agenda for this talk is we'll take a look at what POS systems are and how credit card look. Now, both of these, so POS system and credit cards, it's nothing new. I'm sure most of you have used POS and credit cards at some point of time. But we'll take a little bit in-depth look at the system itself, how it interacts with other components of the module, and so on and so forth. So we'll take a look at POS systems. We'll take a look at how the attack works. For the purpose of this presentation, initially I was thinking of dissecting some of the existing POS malware which exists. So basically take a POS malware, open it up in IDA Pro and sort of go over that. But then to explain it, but that would only sort of explain that particular malware in detail. So to go over the generic things that the malware does, what I ended up doing was I ended up creating my own malware that we will study here today. So since it's like a homegrown malware, we have all the source code. You can ask me all the questions on how it does what, and it's just a lot easier. There will be a demo. So what I have here is actually a fully functioning POS or point of sale system. So I have I mean, you may not be able to see it that clearly, but I have a credit card reader here connected to my laptop, which is actually a POS right now. And I have a bunch of credit cards here. And what we'll do is we will, and I have POS software installed and running on my laptop. So we can swipe some of the cards and run the homegrown malware that I talked about and see how the malware works. And then at the end of the presentation, we'll go over some of the countermeasures on what can vendors do who own POS systems, and what can we do as users of credit cards. So yeah, this is the short agenda. Let's get started. So this is the 2014 Verizon data breach report. Now Verizon comes with its annual data breach report, and it tells you on the percentage of exploits that happened in sort of real life for that year, and it also has a dollar amount on how much data was lost or what did it cost the industry and so on and so forth. So the 2014, so I don't think the Verizon data breach report is out this year, but for the 2014 report, the POS intrusion was pretty much at the top with 75%, so the top part. And again, the slides will be available at nullcon's website, so if you cannot see it that clearly, that's fine. So about 75% of intrusions in the accommodation industry were due to POS intrusions. and that was followed by retail, which was 31%, and so on and so forth. Now, the thing to note here is that this is the 2014 report, which talks about data in 2013. But so when the 2015 report comes out, I'm sure that the retail industry will be 75 to 80%, and accommodation industry will go down because of all the data breaches that happened in the last year. I mean, any vendor you talk about, Target, Home Depot, Credit Suisse, I mean, most big brand companies were targeted and data was stolen last year. So this report will look a lot different when it is released this year. So anyway, POS malware is a real threat, and there is a lot of data to show that. So this is a typical credit card that everyone has. A lot of people in the US have the one on the left, which is called as the magnetic stripe card. And this is the type of card where most of the breaches are happening. The second one is the one on the right has a chip. It's a chip and pin credit card. And the third one on the bottom is your NFC, sort of a tap and pay credit card, where you don't even have to swipe or put your credit card anywhere. You just bring the card close to the machine and then it can charge that particular amount. So we'll talk a little bit, we'll talk more about the magnetic stripe card in this presentation, because almost all the attacks last year were targeting the magnetic stripe credit card. And a lot of you may have a combination of the top two credit cards. So you may have a chip, but you may also have a magnetic stripe behind it. So it really depends. And this is a typical POS system. So when you go to like Target or Reliance or anywhere, do your grocery shopping, when you check out, what you see is that at the counter there is a typical sort of a touchscreen interface. There is a thermal printer, there is a cash register that opens up, and there is a CPU, and there is a card reader, something similar to this. So this is sort of your typical POS system. What's inside that POS system most of the time is basically operating systems that are typically off-the-shelf operating systems. So we have seen a lot of embedded Linux running on these POS, but most of the time what we have seen is they have embedded Windows, or basically there is a OS called as POS from Windows, Windows POS or POS Ready, something like that. So it is similar to, it is the next extension of XP Embedded, and that basically runs these POS terminals. So those were the credit cards. This is the POS terminal. This is what is typically on the magnetic stripe of your credit card. So the magnetic stripe is pretty simple. I mean, if you remember the days of tapes, so I mean, not all of you here are from the MP3 generation, right? Some of you at least have used the physical CDs for your music. And I'm sure some of you have also used the actual tapes which have a A side and a B side. So you put that tape, a cassette, into the cassette player, you hit play, and the tape goes over the head and it plays the song. Everyone remembers that, right? No? Okay, good. Whew. I thought I was the only old one here. So on your credit card, it is a pretty similar tape. You can just imagine as if that tape is sort of stuck on your credit card, and there is a very similar head here like you had it in your cassette player. So in the cassette player, the tape moves. There are these two holes, two reels by which the tape moves. It passes over the head and data is read. Here, since there is no motor, you physically swipe your card, and that basically reads the data in the head which is present inside here. So it is almost the same technology. Instead that the reels move here, you yourself physically swipe the card. So on the magnetic stripe, basically what you have is you have 3 tracks, usually 3 tracks. Track number 1, here let me go back. So track number 1, it is it can store about 210 bits per inch. So this basically defines what's the density of data that can be stored on that magnetic stripe. So track 1 can store 210 bits per inch, and therefore it can store 7 bits per character. So basically what that means is on track 1 you can store 79 alphanumeric characters. Track 2 can store 75 bits per inch, and which therefore makes it basically it can store 40 numeric characters. So there are various different densities of these tracks, and the reason for that is, let's say if track 1 goes bad or there is a little bit scratch on your credit card or things like that, then still data can be read from track 2 and still the transaction can sort of go over. If you sort of do a straight to vertical scratch on your credit card and damage all the 3 tracks, then well, data cannot be read. Track 3 is usually not used in credit card type of data. It is used mostly in hotel cards, or I mean, magnetic stripes are used in a lot of places, right? In hotels, in maybe at people's work when you go in. But for our purpose, for credit cards, mostly it's track 1 and track 2. So the next slide is going to be very busy. And the reason I'm still going to go over that is so that it will give us a pretty good feel of what the malware does and how it's able to steal data. So what we are going to look at is track 1. And this is all public information, so you can pretty much find it in any RFC or any specification. So this is typically track 1, the first line which starts with this %B407 blah 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 blah. That is basically track 1. And at the bottom, the diagram that we have, that is basically the explanation or the data structure by which track 1 is arranged. So for example, it starts with SS, and the bottom, if you see SS, it's start sentinel. So it's basically nothing but some special character which tells the card reader that this is where the data starts. And in case of credit cards, it's the % sign. Then it has a field separator. You know, I mean, most of you have developed some code, some script, so this should not be like too foreign. Field separator is just telling you that okay, there are multiple fields that are that will be here, and this is the field separator. Then what you have is your PAN, or the primary account number. So that's the 19-digit credit card number basically that you see in front of your card. It's also stored on your magnetic stripe. It again has another field separator followed by your name. It's 26 alphanumeric characters. Again a field separator saying that okay, now we are going to a different field. And there it stores additional data which has your basically expiration date, your service code, and so on and so forth, followed by discretionary data. Now this data is pretty important because it has the CVV, or card verification value, or the CVC, or the card validation code, or your PIN basically. So the PIN is basically stored here, and it's followed by an end sentinel saying that okay, that's it, the data is done. So pretty straightforward. You can find this diagram. I got it from this URL that is at the bottom, qcard.com, but you can find it almost anywhere on the net. So that's how track 1 is stored. Track 2 is stored in a similar way. I'm not going to go into a lot of details of track 2, but you sort of get the idea that it's some character that's saying that the credit card data starts here. There is some character saying this is PAN, some character saying that these are the field separators, and so on and so forth. So once you read the RFC, it's very clear. So now let's look at some of the major transaction types. So there are 2 transaction types. One is the card swipe, when you sort of hand over your card to the cashier, and the cashier swipes the card for you. And second is if you buy something online. Now, let's say if you buy something at Amazon.com or Amazon.in, at that time, at your home, you don't have a card reader, but you still want to purchase something using credit card. So there, that is called as the card not present transaction. And oh boy, and a little thing which is a little confusing about the card not present transactions is that on the back of the card there is this CVV number. So this number is different than the number which is stored on the magnetic stripe. So basically what happened was initially, I mean, a long time ago, there was no online transaction. So there was only then one transaction which was card swipe. Everything was on the magnetic stripe. When you swipe the card reader reads it, sends it for authorization, gets a yes or no reply. If it's yes, then it will charge your credit card and then the transaction goes through. What happened with online was that since there is no card reader that you have at home to swipe the data when you're buying something online at home, the credit card guys, they said that, okay, let's put another number here which is printed physically on the card, and let's have the users input that number in the online form, and we'll use that as authorization. So when you swipe the card, the CVV number on the magnetic stripe is used, and when you use it online, the CVV2, which is on the back of the card, is used. So, and these two numbers are different. So your CVV number, like the one here is like 139, that is different than the one on the magnetic stripe. So we'll obviously focus more on the card swipe because that's where all the attacks happened last year. So there has been a lot of talk about encryption and security and firewalls and lot of various infrastructure to protect your credit card data. And all that is good, but it protects your data when the data is in motion and when the data is at rest. So it sounds good, and it is actually good. So it sort of makes sure that the data is encrypted when it is moving. So when you swipe the card, when the data is sent for authorization, it is encrypted and with SSL and the supposedly unbreakable SSL, which is broken many times last year, but still. So data is basically encrypted when it is at rest, when it is stored somewhere, or when it is in motion. But data is still not encrypted in one place, which is in the RAM. So there is a part, or there is a very tiny amount of time, a few milliseconds, few microseconds, when you swipe the data, when the process which encrypts the data, when it is encrypting the data, before the data is encrypted to be sent for authorization, it is still in clear text in the RAM. And all the credit card stealing malware, what they used to do is they used to scrape RAM for this credit card data. And that is what we are going to look at today in the homegrown malware that I was talking about. So it's basically more or less a cat and mouse game, because your POS software, which is doing your credit card authorization, it is trying to encrypt the data in the RAM as soon as possible. But what the malware is trying to do, which is also in the RAM, is it's trying to get to that data before the POS software can encrypt that data. So that's why I said it's sort of a cat and mouse game. Who gets to that data first in the RAM? Is it the POS software, which will read the data, encrypt it, and then send encrypted tokens for authentication? Or is it the POS, or is it the malware which can get to the data before it's being encrypted? So the attack scenario, typical attack scenario, or at least the one that we saw last year, was that a lot of these companies, they have their credit card terminals outsourced for maintenance. And many of the breaches happened because these terminals, they had a remote desktop or other type of remote management services open so that they can be upgraded remotely, but they also had things like default passwords and whatnot, so that attackers could also put their RAM scraper malware on the POS terminal. So the attack scenario is basically somehow the attacker is able to get your RAM scraper malware on the credit card terminal. Then what happens is a customer comes by, he or she swipes the card, and that's when the RAM scraping happens. Is basically the RAM scraper, it starts scraping the entire RAM for credit card. So that's a typical American RAM, the animal, and it's a RAM scraping. So that was intended to be a joke. RAM scraper attack working. So the malware has to be a lot efficient to get to this data, because as I said previously, it's the data is unencrypted in the RAM only for a very short amount of time. So when you swipe the data, immediately the process which receives this data, it starts encrypting it, and the malware has to get to the data before the entire data is encrypted. So what the malware does, or at least what malware that I have created here is doing, is it will find the POS process that has credit card data. Now, to find the process, the easiest way is take, let's say, the top 20 credit card vendors and basically just study their software. So you know that vendor A, B, and C, their software has this thing in the title of the window, or the Windows class that the software registers is this. So there are various calls that you can use, various APIs to find processes. The one that I use is basically you enum processes, then you open the process, then you enumerate the modules in the process, and then you get the module base name. So what these things at the bottom are, these are just API functions. So these are the functions that I have used, but I'm sure, I mean, all of you are good developers, so you can find any combination of functions that could be used. One more thing is, initially I was going to open source this, but then just before the conference I had a talk with my boss, and he said, I don't feel very comfortable open sourcing, you know, a malware program, because the program is still used in the wild to attack POS systems. So unfortunately we are not going to open source this program. But if you have any questions or anything like that, just let me know, and I can answer your questions. And most probably after going through these calls here, you can pretty easily figure it out yourself as well. So the first thing that the RAM scraper does is it finds the POS process. So the RAM's, let's say the malware is already present on the POS terminal. Now it has to basically attack this POS process, which has the credit card data, right? Like most operating systems, they have some amount of protection from one process just attacking other process, right? I mean, we are living in 2015, and it's not like the days of MS-DOS where you know, you could just read anything from anywhere. Yes, go ahead. So the question was that what RAM are we talking about? So the RAM that we are talking about is the system RAM. So this is the card reader, and I think it will be a little bit more clear when we do the demo. So this is the card reader. When I swipe the card, there is a process running, and this is connected to my POS system, which is my laptop. So there is a process here which is reading this card data, and it will try to encrypt that card data as quickly as possible and send it for authorization. And the POS malware is also running on the same POS terminal, and what it's going to try to do is it's going to try to attack the POS process to steal or memory scrape the entire RAM of this POS system to basically get credit card. So okay, you find the POS process, You could alternatively just look at all processes, but then that decreases your chances of getting to the credit card, because as I said earlier, it's a cat and mouse game. The POS software will read the card data, it will try to encrypt it as soon as possible, but the RAM scraper malware has to be very quick to get to the data before it is encrypted. So these are basically just some steps to make it real quick. The second step is to elevate your own privileges. So what the malware does is it elevates its own privileges, and the privilege name that it uses is the debug name privilege. And what allows this to do is that it can call a series of functions which are, I have mentioned at the bottom. These are again API functions, to open the process token, to look up privileges, and to adjust the privilege token values so that it can do this RAM scraping attack. Now if this fails, this is what my example malware does, but if this fails, there are other techniques like DLL injection, where you can sort of inject your own DLL into the POS process and still get to step 3, which is basically you just open the process. And I've just chose this graphic is because after, like, if step 2 is successful, that's a very crucial step. If step 2 is successful, step 3 is very simple. You just open the POS process by calling open process, and basically then you do your RAM scraping, which is basically you read every bit and byte of that process, because you really don't know what is stored where for credit card data. You can use various read process memory, virtual query EX, various different calls and various combinations. These are just the calls and the combinations that I have used. So, okay, this is mostly on the theoretical level. You open the POS process, you start RAM scraping, but again, finding the credit card number in some other process's RAM is like looking for a needle in the haystack. So even if you have done some optimization in finding the process, now you have this bunch of memory that you have to search. Most modern processors, they have a lot of virtual memory. So although the RAM, although you may have like 4 GB or 8 GB, 16 GB RAM, you have tons of virtual memory. And for the RAM scraper malware, it looks just like real memory. So what a typical malware tries to do, or at least what my example malware tries to do, is it looks only for memory segments that are committed, so which have physical memory associated with that particular virtual memory. So it's again one optimization. It ignores memory parts that are for executable image. So when you are scraping the RAM, and in the parentheses what I have is these are various flags. So if you use the mem commit flag, then basically you will get only memory that is committed to physical RAM. If you use the mem image flag, then you will get only the executable image, and that you should ignore, because in another process, in the POS process, the data is not stored in the executable in the code. It will be in the variables section. So you basically ignore the executable image for the POS process. Some other things that you could do is you could try to remember addresses that were successful last time. So now, of course, like all modern operating systems have ASLR, the address space randomization, so that every time when a process is loaded, the variables are loaded in different parts of memory, in different random parts of memory, so that the malware cannot guess where a particular variable is in the memory. So you can do that. And last but not least is you just do pattern matching for track 1 and track 2 data. So this is where that slide that we saw earlier, that comes into handy. So this is track 1 data, and as you can see, there is just a pattern here. So I'm looking for any data that starts with %B followed by 19 alphanumeric characters, followed by a caret, followed by any, sorry, not 19 alphanumeric, 19 numeric characters, followed by a caret, followed by a name which could be alphanumeric, followed by a caret, again your additional data, and it ends with the question mark. So if you have used Perl, Python, PHP, C++, anything, you must be familiar with regular expressions, right? So using very simple regular expressions, you can give a pattern saying that, okay, now don't give me only memory that is committed in the RAM. Give me, ignore all the memory that is part of the executable, ignore all the resources in the RAM like JPEG images and all that for that process, and then give me, and then do this pattern matching. And give me the memory that matches this particular pattern. So by doing this, you will get something. You will get some 18 or 19 digit credit card number. So what most malware does, and definitely my example malware also does it, after it gets the credit card number, it also tries to validate if that is a valid credit card number. And that is done by the Luhn algorithm. And again, this is no secret. If you just Google for Luhn algorithm, you will find that. So what Luhn algorithm says is that when you have any 19-digit number, which looks like this, it's a credit card number. How do you know this is a valid credit card number? So what you do is you drop the last digit. So this is a credit card 4074. It's expired. So you can write it down, try to use it, but won't work. So you drop the last digit. So in the example that you see on the screen, you drop the 5, then you reverse the digits. So we had like 455, and you just reverse the digits. You multiply odd digits by 2. So the first digit was 5, you multiply it by 2, it becomes 10. The second digit was 8, you keep it. You don't do anything with it. The third digit was 9, you multiply it by 2, which became 18. The fourth one was 9, you keep it like that. So you multiply odd digits by 2, you subtract 9 from the numbers that are greater than 9. So if it was 10, you subtract 9, it becomes 1. If it's 8, you just keep it as 8. It's almost like a riddle, but it's actually a algorithm that is used by all credit card vendors and malware to verify if the credit card number is correct. And at the end of the day, you add all the numbers, and in this case what you get is 85. And if 85 and the first number that you dropped, you add those numbers, you do a modulo 10 of those numbers. If the answer is 0, then it's a valid credit card number. So again, it may sound very involved, but actually it's a pretty simple algorithm, and it's used sort of everywhere. The code for this actually is very simple. So like a quick and dirty C++ code that I wrote for this is only this long. So using just a few lines of code, you can determine if this is a real credit card number or not. And I think there are some online websites as well that you just input some number and it will apply this algorithm, and it will say, oh, this is not a right credit card number. Then you try applying your valid credit card number, and then it will say it will tell you that, oh yeah, this is a valid credit card number. Of course, if always remember, when you put something online, the server sees it, so they may very well have your credit card. But yeah, so what the malware does is that it then applies Luhn algorithm to make sure that it's a valid credit card number, and then, well, then it sends it to the command and control, the credit card is stolen. So all right, enough of talk and theory. Let's take a look at the demo. So I hope the demo gods are with us today. So what I have here is basically all the, and again, I'm not going to read code. That's a very bad idea to do in the presentation, but it's a very small, I think 4-page worth of C code that describes the 4 steps that I had mentioned before. Is you You try to be quick, you try to find the POS process, then basically you do pattern matching, you find the POS PID, you get the process number, you apply Luhn algorithm, and then basically here it sort of prints the memory location where it found the card number and the card expiration date and all those good things. So what I have here, where did it go? Okay, so this is a POS system from a very well-renowned vendor. I'm not going to name the vendor, and actually they are pretty good, so I like their software. So let's imagine you are at Reliance, some Reliance bazaar. You do some shopping, you come at the cashier and say, hey, I want to buy this. So before you do that, a cashier usually comes in, he or she clocks in. Let's say my name is Bill. I clock in, so now I am at the cashier. And let's say you bought a bunch of items. So I say make sale. Everyone is sort of getting what's happening, right? This is a POS software, and there are like tons of such software available. This is from the most famous company that creates POS software. So I'm using their software. So what did I buy? Let's say I bought like a baseball hat for $11. Let's say, so I'm the cashier right now. I'm trying to check you out. Usually the credit card terminal also has a reader, so I don't have to manually type what was bought, but for the sake of the demo I'm just manually typing. So let's say I bought a baseball or a ball bucket or something. So anyway, I bought a bunch of items. Let's buy something more. Bat choke. Okay, so I bought like a bunch of items and the total was $33.26. The person, the credit card was given to me. I say credit and it says swipe your card. So these card terminals, these are pretty inexpensive devices. Like I bought this for like $15. And the reason it was so cheap is because it's one-sided, because I have to swipe the card only. It can only read the card like this, not like this, not in the opposite direction. If I had paid $30, then I would have got a card reader that could read cards from both sides. If I had like spent maybe $100, then it would have been a reader as well as a writer. So my point that I'm trying to make is that these devices are very cheap, and anyone can basically buy these. So let's swipe this card here. So it basically reads the card, and now let's see my example. Malware is run. Right now it's not running in the background. I'm manually running it on the command line, but I mean, you got the idea, right? In reality, the malware would be running in the background trying to scrape data. So I just swiped my card, the malware is running, and boom. It took not even so this is the malware process running in the command window. This is your POS process, and the malware process was able to find all the details here very quickly. Memory location, the credit card number, and it may be a little bit difficult for you to read it on the screen because the font is pretty small, but it was able to read the entire credit card number. It was able to get my name on the card. It was able to get the expiry date, service codes, the PIN verification values, PIN verification key, card verification value, everything. Now it's displaying the same information twice because it is currently located 2 times in the POS process. So this information is same. It's just that the memory address, this memory address is different than this memory address. So what happens, or what has happened, that which is my guess, is that this process, it has read the credit card information, it has stored it in some variable, and most probably it has passed it to some function. So when you pass the information to some function, a copy was made of that information, and that copy is somewhere in the memory. And again, I don't know the internal details of this POS process. What I just get is just zeros and ones, and based on what we talked about before that, I just get a chunk of memory. I just do these regular expressions and try to then apply Luhn algorithm and just get the card number. So I mean, the malware doesn't have to know how the POS process is structured internally. It just gets these zeros and ones and tries to extract the card number. So yeah, I guess the demo worked. So at this point, I mean, my malware just prints the information on the screen. A real malware would send the information to command and control, and there goes your credit card. One other interesting thing is, so here I say no tip, and okay, so the transaction went through. So now if I run it again, it was not able to find it. So what happened was that this POS program, it's not that bad, as in after the transaction went through, it was able to it did clear out its memory, and now no matter how many times I run my malware, it's not able to find it, because the POS program has at least taken that care that when the transaction goes through, it writes zeros or ones, or it basically clears the memory for those variables. So it doesn't like depend on some Java type of memory clearing where your memory gets cleared only after automatically. So it manually does write zeros or ones or something to the variables, so that to make sure that even though it is not using the variables, others or such a malware cannot get to it. So not bad, but that's how your credit card usually gets stolen. So let's get back to the presentation again. So mitigation. So what can we do to protect against such attacks? Well, the POS business owners can do a lot, or actually they are the only people who can do most of the things, is use POS only for the intended purpose. So the breaches that we saw was because the POS terminal, which is like right now it's my Windows box, but a real POS terminal also can be used to send emails, to check your Facebook account, to do anything. You can just stop the POS program running on the POS terminal, and then you can do whatever you want. It's almost like a regular operating system. So one thing is use POS only for the intended purpose, so that the malware doesn't get there in the first place. Secure remote management software for POS, RDP, VNC, and others have measures to protect against insider threats. A lot of times we saw that in places like 7-Eleven or in smaller shops where the owner of the shop is not running the business, it's some other guy running the shop. People would just come and say, hey, put this USB stick in and I'll give you like $500, and the person just sticks it in, which infects the machine. So even such low-tech type of attacks do happen, and we have seen them. Best practices: do access control, vuln scanning. There is a lot of access control available in a lot of operating system, but most of the time in real life, many programs or practitioners do not use it. So make sure all that is in place. Enable end-to-end encryption-based devices. So this device, it does not have end-to-end encryption. There are devices which are a lot more expensive, where the encryption happens here and not here. So that is a lot more safer, because when you swipe the card, just the encrypted tokens get passed here. So if the POS business owners have the budget for it, don't use these cheap type of devices which usually are just stuck here. Smart cards, yes, smart cards are a lot safer than magnetic stripe cards. And finally, the POS vendors is they can basically encrypt the data quickly from the memory, use built-in encryption support. We saw some of the POS software vendors, they were trying to do their own encryption. And encryption is such a thing that you should always use some existing library or something like that to do it. Don't reinvent the wheel. Don't try to do encryption from scratch. So those are some of the tips that we had for the POS software vendors. So I guess that's it, folks. We looked at POS terminals, we looked at credit cards, we looked at magnetic stripes, we looked at how the malware does, how it's able to extract credit card information. The demo fortunately worked. And we still have about 5 minutes left, 5 to 10 minutes. I would like to open it up for questions.
Hi, this is Anudeep from Symantec. So how does smart cards ensure that this kind of attack that you explain does not happen on them? What sort of security does a smart card provide?
So if you have the chip and pin card where the chip is on the card and you do not have the magnetic stripe on the card, I mean, a lot of times you get a chip, but there is also a magnetic stripe. So then that sort of defeats the purpose, because it then depends on the card reader. If you swipe it, it will read the magnetic stripe. It won't read the chip. So if you have a chip only card where you don't have the magnetic stripe, and if you just have the chip, then basically the chip has, when you use your chip and pin cards, the credit card number is never really transmitted. There is a one-time token which is transmitted, and that basically authorizes or does not authorizes the card. So the chip itself, the chip which is on the card, does sort of the transaction for you. Does that sort of make sense? I mean, chip and pin is a pretty involved technology, and I don't think I can explain how chip and pin works in the next even 5 hours. But basically, you can think of it as all the encryption happens on the chip in the card reader. So that's the reason it is it's safer.
Thank you.
Hi. Nowadays, a PIN is mandatory for the transaction. So how useful the data is for an attacker?
So in chip and pin cards, and I would have to say that a lot of, Europe uses chip and pin, and I think India uses chip and pin, right? I mean, as you said, chip pin is mandatory. So that is very good, because that makes, basically when you enter the pin there, your credit card number and none of the credit card details are sort of transferred, or there is only a one-time token that is generated at the terminal, and that is passed to the bank for authorization. So that makes it a lot more safer. Unfortunately, in many other countries, I would say in many other underdeveloped countries as far as credit cards are concerned, like the US, chip and pin is not being used yet. So all the cards that I have are without a chip. So the chip, yeah, that was actually the main reason for all the data breaches that happened last year. Yeah, so if you have chip and pin, then I think you are pretty much safe as long as you don't have a magnetic stripe on your card. Although chip and pin has also been compromised, so there was some research done at the University of Cambridge, and they were able to also hack or basically break into the chip and pin technology. But then that requires a lot of, it is a lot more harder than to break into normal magnetic stripe based cards. I hope that answers.
Thank you.
All right, any more questions? No. All right, we're taking the last question.
So we discussed about this scenario where the card reader is not encrypting the card. So is the solution certified by PCI Council?
So yeah, I mean, most card readers in a lot of countries, at least in the US, as well as I still see a lot of such card readers even in India. So yeah, they are certified by PCI. So this is how credit card business was.
Because PCI Council says that you should be encrypting the card data as soon as it arrives on this system. Okay, so in this case, what is happening is that when you're swiping the card at the reader, it is going unencrypted to the system, and there you are doing the encryption. Okay, so there is a certain time amount of time where the card data is still in plain text. Okay, in the case of hardware POS terminals, where the card is getting encrypted in the hardware module itself, and then it is coming to the application, and then it is going. So obviously, your application doesn't need to be PCI certified. Okay, because it is not handling the unencrypted data; it is handling the encrypted data. But in this case, the application needs to be, or the terminal needs to be certified, and you're saying that it is being used for a general purpose as well.
I sort of got your question. Now again, I have not really read through all the documentation of PCI certification. The reason I can say sort of that it's PCI certified because in the entire US that's how it happens as of today. So even in the US they are trying to move towards chip and pin cards by the end of this year because of these major hacks last year. But that's how it's happening, at least as of today. So as I said, I haven't read all the PCI certifications, but I think it's PCI certified because that's how transactions happen, at least in the US.
Thank you.
All right, thank you. If you have
you.
any questions, you can just ask me on Twitter, and I would be I'll get back to you. Thank you.